Start
This
that
conference
recording.
will now be recorded.
Again, if there's any questions out there, please stop me along the way. So there's a number of trends that we have seen in satellite data and in the world that have pushed us towards data cubes as a technical solution. So open source software is the cornerstone of everything we're doing with the data cube. So though we have an abundance of satellite data, we are using everything in the data cube as open source and free and open to you. So there's no fee associated with any of this material. We've noticed a big push in global engagement. So there's been improved communication. I can talk with you today in Tanzania, and we can collaborate and cooperate in so many ways. Philanthropy, you may or may not know that Amazon Web Services and GPSDD, Global Partnership for Sustainable Development and Data, have been the primary funders and pushing this forward, this idea of the African Regional Data Cube. So all of this has come together, and now we're at a point where we can compile this data from many of these Landsat scenes and put it together in these things we call data cubes, and that's how we interact with the data and the information. So we have all this in place. The problem still becomes there's some scientific knowledge needed to understand how to use the data, because we've got optical data, we got radar data. There's a lot of problems with accessing and downloading. The data is hard to prepare, and we have to do things like we're doing today with training and capacity building. So we think that what's happening with the Data Cube initiative and the African Regional Data Cube solves a number of these problems, and that's why we're excited that you're going to have this potential to use it and make it available for your use cases. So let me tell you a little bit about expectations and what you might be able to get out of this data cube. If you were to look at the scene on the right from space, which is a scene of a baseball field, or that could be a soccer field, those little squares you see on the left are what we call pixels. And in the case of Landsat, the size of one of those pixels is that little square that you see there. And notice that what you can resolve in those pixels is only 30 meters square. So I will be able to tell where the grass is in the infield. I might be able to tell where the infrastructure is, which is that area that's white, but you notice things get blended a little bit. And so that's part of the nature. We have to understand the resolution of what we're using here, and that sometimes we can't resolve very small features. We can resolve larger features in all of this. So that particular scene I showed you in the beginning, which was one Landsat scene, and you're looking at it here, has 35 million of these pixels. So there is a massive amount of data in even one of these Landsat scenes, and imagine now pulling this all together and giving this the ability to see your entire country at that 30-meter scale, so I can see all the pixels of that small size across your entire country. That's a very powerful resource. So let's talk about what this thing is that we call a data cube. So imagine if we take 8,000 scenes, which is 17 years worth of data, and we pull all of this together. We can take those little building blocks out of those scenes, which are called pixels. We can stack them together like you see there in the top right corner, and we call that a data cube. And we then put this in little storage blocks like 1 degree by 1 degree by 1 year. That's fairly arbitrary. And then we compress that data down, and then we create what's called a cube. So instead of dealing with the scenes on the left, we now have all the pixels stacked nicely in this thing we call a data cube. So let's talk about how you can query this cube in various levels. So first, um, if you think about the cube as latitude and longitude extent, and it has time extent. So think of it as three-dimensional space. If I were to pull out a single time layer, that might be similar to what you saw in that prior thing. That could be a scene. So that might be a single point in time. I can pull out a piece of that cube. I can do an analysis in a certain lat-long region for a certain period of time, a single day. And that's one way to think of the cube. Another way to think of it is, what if I were to combine a few time layers? So if I pull together multiple time layers in we call these time slices, that ends up being something we call a mosaic. So it's often used to filter out clouds or put things into annual images. And we typically do things like looking at the most recent pixel, or we might do a median, which is sort of like an average of the data of the pixels, or something like a vegetation index that's maximized. And then finally, you could carve through in time. So if I went through a long time series and I just did a small spatial region for a long time, I might be looking at change. So I could look at land change, or I could look at water change. So think about this cube. You should always think about this cube in your mind as having spatial extent and time extent as a three-dimensional stack of these little things we call pixels. So I'll stop there for a moment. Are there any questions out there? Everything good so far? All right, let's keep diving ahead. So what are the benefits of these cubes? We know that we're going to be able to use satellite data more if we have it prepared in this way, because the data preparation burden is significantly reduced. We know that we can use data interoperably, and by that we mean we can pull together different data sets. So if I wanted to use Landsat data with this data from the Sentinel mission that the Europeans have, I can stack them together such that we can use them together. And if I stack my Landsat scenes nicely, I can do time series analysis because all the pixels are aligned in time. So everything we're doing with the data cube is free and open access. As I said, it's open source software. Flexible deployment. We can put the cube, as we have for your case, it's in the cloud, but it could be done locally as well. And it's proven in a number of countries right now, and certainly now in Africa. So our vision was to build capacity across the world to use our satellite data from all these agencies. United Nations and GEO, they're all quite interested in this. We want the data cube to be something that's easy to use, maintain, and to train people on, and that's why we're doing this training now. And it's a scalable solution because we want to be able to go into many countries, and we're developing partnerships with people like Google and Amazon. So just to give you an idea, this is where the cubes exist around the world now. So it's nice to know that even though your 5 building blocks, your 5 green building blocks in Africa are the countries, including Tanzania, there's also many more around the world. So when Vietnam comes up with a new algorithm to do something interesting, or Australia or Colombia, all of which have operational cubes, they can share those algorithms with you, and you might be able to use and take advantage of those same algorithms. So one of the values in what we're doing here is pulling together the tools and the mechanisms and some of the new features and advancements to make your job easier in the future. So that's one of the goals. So when we do all of this, there'll be a number of application products that we can apply to the cube. And this is just a list of some of those algorithms. I already told you a bit about cloud-free mosaics, recent pixel, median, max NDVI. There are things like spectral indices. We can look at vegetation indexes. We can look at buildup index, which is an urbanization. We can look at water, fractional cover. all of these indices are just basically what we call band mathematics. So if I take Landsat band 1 and Landsat band 3, I might do some mathematical manipulation and come up with a fancy thing that I call an index. Land classification, I can cluster land types such that I can apply classification. So if I want to know where the agriculture is and I want to know where the forest is, I might do some land classification. Water is always high interest. So we have a water observation from space called WAF's algorithm that was developed in Australia. We have one for radar, and then we have one that can look at water quality. So there's some really good water algorithms that are quite interesting, and I'm going to show you a few of those. And then finally, land change. Land change is probably, next to water, land change is probably the other one that's the most readily requested. So we have a number of interesting algorithms there. PCA from Columbia and USGS has one called PyCCD. Those are pretty intense. I'm going to demonstrate for you in the next couple days some things we're doing with vegetation anomaly and vegetation indexes. So those are all quite interesting. So the summary here is that we have a group of algorithms that you can apply to the cube. And in some cases, if you have an application, or let's say you have a use case that we don't have an algorithm for, it's in our best interest to help you develop one and to try to get you to a point where you can answer the question you have about your data. So I wanted to share with you some use cases around the world so that you get an idea of the kind of things that can be done, so that you might be thinking from Tanzania's perspective what it is you'd like to do and how you'd like to use this cube. So in Switzerland, they developed a new snow detection algorithm using time series data. So certainly for some of the highest peaks in Tanzania, this might be of interest. UK REA is a commercial company that is using the data cube to create a drought monitoring system in Uganda. So since the data is free and open, it's possible for any commercial entity to also connect and to start to use the cube. UK Catapult is another group. They're linked with the UK Space Agency, and they're running a project in the Pacific Islands. Taiwan is using the cube for forest and vegetation studies, and they're looking at another algorithm for an interesting one on pine beetle outbreaks, which looks at deforestation due to pine beetles. Uruguay has been using the data cube to adjust their water sampling in their reservoirs. So if you were able to look at the water quality across a large reservoir, that might impact how you sample the data in time, both exactly when you make the sample and where you make the sample. If you have some satellite data to help you, it will drastically improve your sampling mechanism. And then Gates Foundation, we developed something over Lake Chad to help them out for monitoring some of the small villages around the lake. So let me stop there. Are there any questions at this point from those online? All right, if not, I'll continue right ahead. This summary here is a recent chart that I put together. Maybe some of you will see your faces in the bottom right corner. We had the African Regional Data Cube initial workshop in Nairobi, and it was attended pretty broadly there. There's probably 50 people in that photo. And it was a nice start to kicking all of this forward. Since that time in May, we've worked on trying to get a better handle on the use cases within the various countries, what algorithms and what problems you have and what algorithms can we apply. In the background, we're working to build the data a little deeper. So we want to get you more Landsat data up into the cube, and we want to be adding this new Sentinel data, Sentinel-1 and ALOS, which are both radar data sets, will be coming very soon. And so you'll find those interesting because radar can see through the clouds. So many of the countries that we're dealing with in the equatorial Africa have a lot of issues with clouds. So if we're entirely relying on optical data, it can be somewhat limiting. I did remote web-based training as I'm doing this week with you in Tanzania. I've done something for Ghana. We did something for Tanzania back in August, a single day. We're doing a few days here this week, and Sierra Leone. Initial support has been, again, focused on algorithms in these use cases. So Kenya, just to give you an example, they were interested in the refugee camps. They were interested in deforestation and then vegetation. And we even did a specific use case for a rangeland study for the Livestock Institute, where they needed a particular vegetation index out of the cube. And we created them a mini data set with just the vegetation index that they wanted. So in Tanzania, since I've been working with you and discussing your use cases, some of the ones that have been immediate have been the forest reserve, the deforestation around some of your forests, and what I will call agriculture phenology, which is basically the cycling of agriculture over time and the growing patterns of various agriculture. And when I show you either tomorrow or the next day, we'll show you some live examples of agriculture phenology, and then we can start to discuss how you want to use that data and how we might adjust these algorithms to better serve your needs. Ghana was interested in illegal mining, and you can see on the right, I'll just bring to your attention these two figures here. On the left side is a river network here in Ghana prior to illegal mining, and on the right side you can see the situation with illegal mining. So what has happened is when they do this illegal mining, they go in and deforest first, so it becomes a bare land. So that's the red, it becomes bare soil. And then you can see the expansiveness of all of this, and most of it gets connected to the river system because they mine out whatever products they want, they put it into the river system and ship it down to take it away. And it ends up creating a fairly large devastation of the land, not to mention contamination of the water in the area. On the bottom, I wanted to show you this particular one on the bottom left is a complicated water coastal region near Sierra Leone where they've had some inland flooding, and I'm going to show you how to interpret the data there. And these two figures here in the middle are urbanization over Freetown in Sierra Leone. This on the left is actually a different online resource, and this is the data cube analysis of the same exact time period. And you can see that the data cube gives you the same kind of structure for urbanization. So it's very good to know that the results we're getting out of the data cube match what someone else has calculated. And I think this one here is actually done with a complicated and expensive radar system, and this one is done with your data cube. So here's a more detailed one of the illegal mining. I'm just going to show you now a few examples of what can be done. So again, this was year 2000 in Ghana along this river network, the Ankobra River. And here is the details of the illegal mining. So you can obviously see it here, illegal mining occurring along here, and it tends to pop up as little small circles where they do the mining, and then water, contaminated water, ends up coming to the surface afterwards, and there's a lot of deforestation. So if you were to compare year 2000 to year 2017, just from a vegetation loss, this scene alone lost 13% dense vegetation in those 17 years, just in that area. And now if you look at the Google Earth image on the right, these were the areas of the little pinpoints were the areas of illegal mining that were identified by the Ghana government. So it's quite obvious we were able to pick those up. So there was a spot here. I think the spot was down here and another spot up in this corner. We definitely picked up all those regions quite well. So this is a hard one though. It's kind of difficult to see some of this from space because the water, when it gets contaminated, starts to look like bare soil because the water is so dirty. Next is the East Shenane. I don't know if I'm pronouncing it correctly, but I'm going to say East Shenane Forest Reserve in Tanzania. So we performed a analysis, and this was done a couple months ago, on the boundaries of this forest reserve. So the forest reserve is here in red. This is the whole forest reserve. And what we did is we ran some analyses on the fringes and looked at the detail of the pixels. If you did an analysis for the whole region, it would take many, many hours, if not days, to run. If I do something on pieces of this and just look at some small areas, I can zoom in on an area about this size, which, remember, these pixels, these little dots, are all 30-meter scale. This in the top is a product called Global Forest Watch. This is Matt Hansen's prediction of forest loss. This is available on the web. Nobody knows how he does it. The algorithm is not public, but it's a prediction of forest loss. So if you look at the forest loss over those 4 years, and now go down here and compare it to, I colored everything in orange and red was the same 4 years, you start to see similar things. So don't worry about the green because that was their forest mask. But if you just look at the orange and red, this area here coincides with this. This area in here coincides with the orange here. So what this data cube algorithm is saying is we're detecting a lot more land change in these areas. And then the color scheme actually is the timing of those changes. So I think, depending on the year, it colors it. Here it just says everything that's happened over the 4 years is pink. So I just want to give you an idea. This is an example algorithm. Oh, go one more. This one. This is the urbanization algorithm, Freetown, Sierra Leone. So urbanization can be tricky to pick up. If you run a simple urban index like normalized difference buildup index, NDBI, sometimes it works well, sometimes it does not. You have to really just test it and play with it and compare it to some known data. So the case that I ran here for Sierra Leone, and you can do this for Tanzania in any spot you want. On the left is the year 2000. Everything in red is urbanized area, so it's basically picking up the optical scattering that looks like buildings and roads and infrastructure. And look at the difference in 2017, the growth, quite a significant growth. So the urban extent difference between these 2 years is 11% over that 10-year period. So this can be calculated. We have developed and I'll be showing this to you in the next day or two. We've developed something that does this directly. So I'm going to stop there. This is just intro to the data cube. I'd like to use this time to entertain any questions you might have, take a little short break here before we dive into some demos to show you the two tools. I'll stop at that point. Any questions?
Brian, Mark.
Yes, for those of you that aren't speaking, can you mute if you're not speaking? I don't know which person was trying to connect. Thank you.
Okay. Good afternoon, Mark. Brian, sorry. Good afternoon, Brian. Simski.
I'm sorry, go ahead. Yes, is this George Meringue?
I'm Benedict, of course. I'm using the meaning iPhone.
Ah, very good. Okay, Benedict, go ahead.
Okay. Yeah. But if you can listen,
Getting some feedback. Somebody, if you're not the one asking the question, can you please mute?
I have to change. Okay. I have to change the position and then I'll be coming to you.
Nimeshazima mic. Nimesikia tu.
I'm gonna mute George. Let's see if that works. All right, who's the caller that was asking a question? Is it caller 1? Well, maybe not. All right, who is online that was asking the question?
No, it's okay. Can you hear me, Brian?
Yes, loud and clear. Whoever that is. Yes, very good.
Yeah, I'm Benedict.
Yeah, Benedict, how are you?
Fine, how are you?
Good, thanks.
How is injuries? Okay, I have one question is that when do you keep updating this data in the data cube? When do you keep updating the data which is available in the data cube? That's one question. The second one, I don't know how flexible are you, because today we are many and there are some of our colleagues that are from different government institutions, including the Minister of Natural Resource and Minister of Minerals, and others will be coming by tomorrow. They'll be coming from the Minister of Industry. So I think probably maybe sometimes, is it possible for you now at least to create a sample example on something like minerals, because they are really interested to see on how also they can have the data from the ARDC data cube, and then they can make use of that data to analyze the data and then to come up with some of the problems and the solutions as well. Thank you.
Sure. So when you say minerals, the only thing I've seen thus far that is connected to minerals would be the mining operations. So if you think about what you can see with this satellite data, remember back in the beginning of the presentation, what you can resolve on the ground is something that is 30-meter scale, right? Like the size of a house or multiple cars. So when I'm looking at minerals on the ground, what I'm really looking at is some kind of land feature. So describe to me what you mean by minerals. Is it looking for mining activity? Is that what you're thinking?
That's very fine. Good.
Mining activity. Okay.
Yes.
So yes, we do have some of that. So what I was showing you back at this point, the one that we did right here in Ghana is one example of that. And I can show you a few examples of, we can use some indices, which are some spectral indices like fractional cover or some of these vegetation NDVI, and you can look at changes. And the way that we normally do detection of the mining is we do it by looking at land change. So look at this on the screen. This is a Google Earth image over here. You can see the mining activity because the land has been cleared. And so what has happened is over here in 2000, everything along this river was nice and green and vegetated, and then suddenly there's these large changes. So this little index called fractional cover, and things that are red are bare soil. So what's happened is I get this combination of now bare soil surrounding areas that used to be vegetated. So that is one way that we can detect the mining activity. So I can show you exactly how to do that, and we could look at a few areas within Tanzania, and we could actually show you how to do a bit of this on your own just to test it out. Is that what you're thinking?
Yes, perfect.
Okay, good. And so, all right, so that was mining. You asked about updating the cube. Are you meaning the satellite data that goes into the cube? You were wondering the process for getting new data? Is that your question?
Perfect.
So as it is now, I think the data goes through 2017. There might go into early 2018, I forget, but we're in the process of doing two things and working with Strathmore University and people on the ground that are going to be managing the data cube moving forward. So we want to add data that goes back a little deeper back into 1985 for Landsat 5. That's one thing we want to do. And then we want to add new data for 2018. Now, if we get this all working well, which right now it's not exactly working well, we need to get the Strathmore people focused a bit, and a technical person, GPSDD, is going to be contributing a technical person that will help us get this moving. This will give us an opportunity to get data into the cube routinely, probably just about every month. So let's say, September, the month of September just finished, we would have all the Landsat data from the month of September in the cube within a few weeks after the month ends, maybe even just a week after the month ends, because the satellite agency pre-processes it. It takes them a few days to get it going. They put it out on their network, and then we grab that data from the network and add it to the cube. There's much of that process that can be automated, and that's what we need to teach the folks how to do to update it, because you should have the latest information in the cube. You should be able to look right now. If things were done properly, you should be able to look right now at data from August and September of 2018 in your cube and be able to look at the latest, let's say, mining activity and run analysis cases. That is not the current state, but it is something we have to get in place. Any follow-on questions there? Did anybody else want to comment?
Yeah, I have a question.
Sure, go ahead.
Yeah, the topic just mining is Wanjala. I'm from the Ministry of Natural Resources. So when I was following your presentation,
I can't quite hear. If someone could get closer to the mic or maybe repeat the question. I can't understand it.
Wait a bit, Brian. Wait a bit.
Okay.
Few seconds.
Sure.
Brian,
Yes.
you now hear me well?
Perfect. Thank you. Thanks for coming closer.
Maybe this computer is good. My question, when I was following the presentation, I saw one of the examples of the Chinene Forest Reserve. And my question is, do we have data for example, for deforestation issues for all the forest reserves in Tanzania, so we can get access and probably try to track or to understand how is the level for our nature reserves in Tanzania. So is the cube having all the data in it, or we need to probably add more, or how is this probably is my question.
Good question. The short answer is yes, the data is there.
Yeah.
It is there through the year 2017. So any deforestation that might have occurred in early part of 2018, we don't have that there yet. So what I would like to do in the next day or two, and this is why it's good to have this conversation now, because I can tailor what I teach you in the next couple days. I can show you how to reproduce this analysis that you're seeing on the screen right here. And the other thing I'm going to show you is how to do it a little more rapidly with just looking at something called a vegetation index, if you're familiar with NDVI, which is normalized difference vegetation index. It basically shows you greenness. So if something is deforested, obviously its greenness will be reduced. And so you can do some pretty large scale, more rapid deforestation studies using NDVI. The algorithm you see here on the screen is fairly complex, and you have to do it with fairly small regions. I can show you how to do it, but it's something you're going to want to run on your own to try out, because it takes, like this analysis you see on the screen here for this little part of Shanine Forest, that probably took 20 minutes to run that case study. Well, it's not a good idea for us to do that on the fly, but I can teach you how to set it up and how to run it. So we'll do that. I'll look at some other forest reserves in Tanzania. I was given some in the region. Itisu was one. There was another area, I think, that they recently gave me some information. So I'll show you how to do that.
Okay.
And then what I would really love is that once I show you how to do this, I'd love for you to go in and try to run some case studies on your own. We'll teach you how to do that, how to create these products on your own, and see where to go with them. And we can help you. So if you're running an analysis case and it's not running to your satisfaction, or you want to know how to set it up differently, or how to get the product out, like a downloaded GeoTIFF solution, we'll show you how to do that.
Thank you.
Any other questions there?
Yes, I have a question.
Sure.
Do you hear me properly?
Yes, I can hear you fine. Go right ahead. Thank you.
Yeah, I'm Asman from National Bureau of Statistics.
Excellent.
I'm Asman from National Bureau of Statistics, Tanzania.
Okay, thank you. It's good to hear someone from the statistics area. So yeah, I look forward to your question.
Okay. In your presentation, you talked about the urbanization in Freetown, Sierra Leone.
Yes.
And there is a clear evidence that the African cities grows very rapidly.
Yes.
Hello?
Yes, go ahead.
You said that you use the NDBI to detect this growth for 17 years in Freetown. And also, Dar es Salaam grows very fast.
Yes.
So how did you use this, and what is NDBI, and how did you use this NDBI to detect this type of growth?
Okay, so, and this is something I'll share with you in the next day or two. So what we'll do, and we might be able to look at it briefly today a little bit, but I have an urbanization notebook. Basically, it's some Jupyter Python code, and I'm going to show you actually how to do some of this using the online user interface also. But okay. So in short, NDBI, normalized difference buildup index, and I've got a few charts to show you what this looks like. It is a ratio of a few bands. So these difference indices are the difference of two bands divided by the sum of those two bands. And basically, it gives you an indication of urbanized area tends to look like bare soil or bright objects from space.
Okay.
So if you look at this area here in Freetown, this area right here, back in 2000 was forests.
Yeah.
And it was deforested and urbanized, and then it becomes red because now it turned from a dark object in space, like dark green veg, to something that was bright and reflective like an urbanized area. So what
Yeah.
happens is the optical bands can actually detect that change, and that's what you're seeing here. So
Okay.
I will tell you, any of these algorithms are never perfect, right? It's just really hard to detect perfectly things from space because, every once in a while, bare soil might be actually a really dirty reservoir. It's things from space can be confused at times, but I will say this does a really decent job of getting at these growth rates because you can easily see areas that have been deforested or changed from vegetated land to non-vegetated land, and it pops out very clearly. And so if I just count all of these red pixels on the left and compare it to the count of the red pixels on the right, that is how I got the 11.4% growth. And so you can do this over any city you want. You can do it for any time period you want, and you can start to see the change. Here is where I would say you have to be careful, is that if you know particular areas are urbanized, you know where the buildings are based on some visual imagery or some photographs that have been taken or something like that, you might want to compare the urbanization results with some of the some of your ground data, just so that you know that the information you're getting from the satellite imagery makes sense, because you can't always believe everything you get out of an algorithm, right? It needs to be, you have to understand it a bit and test it. But I would argue that for change, like you're seeing here, large scale change from year 2000 to year 2017, I will bet that's pretty darn close. I will bet that 11% change is not far off. So it's this kind of information I think is quite valuable because you can really start to see the growth. You can see the change in the loss of vegetative properties over time.
Okay.
So we'll do that. So I'm hearing a few things that we need to do in the next couple days. Mining
Okay.
activity, forest reserves, urbanization. Those are of high importance to you. Did I answer your question a little bit about the urbanization?
Sure. Thank you.
Okay, great. I'll make sure that we concentrate on that a bit, and hopefully, if you are here in the next couple days, we'll spend some time on this urbanization idea, because I've been working on this one pretty hard because there's a number of algorithms. NDBI is one of them. There's 2 or 3 others that you can play with to see, do they give you better results? Do they make sense? And again, you just have to compare them. What I like to do is I like to go out on the internet and find urbanization maps that someone else has developed. So like if someone spent a whole lot of money developing an urbanization map for Freetown in the year 2000, and they've created this map and I can see that map, that's exactly what I did. I'll show you, let me go back to that. Right here in the bottom, which is this area right here, that grayscale urbanization map I found online. It was done by the Germans, and it was done using a German radar satellite, and they did this urbanization map. Well, I said, well, if I can compare their map to the same exact time period with mine, it'll give me an idea of the accuracy of the result. And I was very pleased with it, because if you see the dark black in this one compared to the red in this one, they're quite similar. So I felt very confident that the urbanization algorithm we had was fairly accurate. It was doing a good job when compared to someone else's product.
Okay.
So that's what I tend to do, because a lot of times you don't have ground data for urbanization in many cases. It's pretty much a guess. You know the buildings are growing, you know the area is expanding. You might not have a real good map of urbanized extent, but if you go out and you search on the web, there's some products out there that people have created some of these global urbanized maps, and it's just good to compare some of those because they may do it for just 1 year. I think this one in the bottom left was like 2014. So that's what I tend to do is compare it to other people's results to make sure that we're getting something that's reasonable.
Okay. Thank
Any
you.
other, sure, any other questions out there?
Hello.
Yes.
Yeah, so this is Jeremy Dufour from Olam, Tanzania, and I believe like the piece of work that actually has been involving also deforestation was the one that we have been discussing with Rose from a company called Aviv Tanzania. First of all, I mean, I would say that the African regional data cube for a private sector such as Olam International opens like a massive opportunity to really measure the impact in terms of social impact and natural impact to the operation that we have. We are specialized in agriculture and trading of agro commodities. So that's definitely something that we look forward to develop. I apologize, but I did not receive like I did not meet. Sorry, I did not attend the first few minutes of the presentation. Could you just remind us? So we do not have personally like GIS expertise in house, and we do understand that this data cube is available online as open source data, but when we do not have the technical expertise to run these filters and etc., would you advise that it would require like a company like Olam to invest in recruiting GIS analysts? Or do you think it's a layman tool that would be accessible to everyone?
Yeah, so when I'd say in the next 5-10 minutes, I'm going to give you a run through of two tools that we use. One is an online user interface. I'm going to jump up to this now, but we use an online user interface where the algorithms are hidden, and it allows you to run test cases anywhere you want you could probably do some vegetation detection. You certainly do vegetation detection. We can do some urbanization. There's a number of products that you can generate with the online user interface, but all the algorithms are kind of buried and behind. So it's better for like a novice user to use the online user interface to run some sample cases. It's interesting. It's a little less numerical and a little less detailed. If you want the real power in the cube, we do these things called Jupyter notebooks, which allows us to get into the code where you actually develop your own algorithms and you have a lot more flexibility in the details of the output products and the area analysis and various calculations. So I'm going to show you the two examples, and I think that'll probably answer your question of how you would use the cube. And I'll say probably first you'll want to go to the online user interface and test it out. And then if you become a little more knowledgeable, if you are a GIS person, I would say it does take some GIS skills and a little bit of expertise to know how to use the Jupyter notebooks, because you've got to have a little better knowledge of what are the Landsat bands, what are the indices and the algorithms, and how do I manipulate this data to produce a relevant product. That takes a little bit of GIS knowledge. Did you say you were from private sector?
Yes, we are from the private sector, yes.
Excellent. So one of the nice things about the Open Data Cube is that it is possible for private sector to access, because all the satellite data is free and open. You could develop your own user interface on top of the cube to develop, a specific product. Let's just say you wanted to create this agriculture product and it was this specific algorithm that you want to run anywhere in the country at any time, you could build that into a little user interface that sits on top of the cube and allow you as a company to generate these products at any time and provide a specific product for someone. So there's a lot of flexibility in this from the commercial perspective, which I think is pretty exciting. So any other questions? These are all excellent, by the way. It's good to hear feedback from you regarding the applications and what your interests are, because that will help us in the next couple days, where we can spend some time focusing in on these things, where we teach you a bit how to do it, and then we'd actually like you to go run a few test cases as well and play around with the system a bit. Okay, if there's no other questions at this point, what I'd like to do is just take a couple-minute break where I can go refresh my water, and we will come back in 3 or 4 minutes, and I'm going to walk you through the next set of charts, which will show you the online user interface and the Jupyter notebooks. Yes?
Before you do, I just wanted to make an announcement. So I've sent a form through which I would like to collect information about everyone in this meeting. Please make sure that you fill it. I've sent a link through the chat, so everyone of you can access it from the chat. Thank you.
Here, yes, so those of you on GoToMeeting, there it is, the chat. This is it, right, Rose, right here. It says, from Rose to all, hello everyone, registered your information here. So she's created a Google form. So everyone should take care of that. And maybe we could do some of that during this little 5-minute break. So let's do that. Let's take a short break. And I'll be right back, and we'll dive in a couple minutes. Sound good?
Good.
Okay, thanks.
Thank you.
I'm going to turn my screen off here momentarily just to fill out Rose's form, and then I'll come back.
Okay. Uko vizuri, dada yangu, uko vizuri sana. Umeshatengeneza na form tayari. Kawa inakuja saa 12 tulisema. Si baada ya nani? Jamani, ratiba umeisoma? Someni ratiba. Kwa hiyo tutabadilisha sasa. Yaani kwa siku ya leo, tupeane tuieni radhi. Sawa. Umeelewa? Tuje kawa saa 1 tukienda kwenye tusilale. Kwa siku ya leo tuieni radhi. Okay. Okay. Yeah, of course, yes. Yes. Can we know how many we are following this year? Tunaofuatilia mafunzo ni wangapi?
Yeah, so you can look at who has logged in.
So far,
like for now, Brian has logged the meeting, so you can't see. But when the meeting is on, you should be able to see how many people there are. There are about 23. Lakini kwa sababu kuna watu walikuwa huko nje ya blog wako, lakini so that's why
23 plus 1 2 3
plus 3 people are there are about 26.
Na kusafiri unapewa ila kule unafanya retirement.
Anasema
Hata
kwanza
hoteli.
anawaanzisha system.
Unapewa impress.
Anaele mfumo wake na track watu wameenda. Bwana Jumani leo umeandika siku 5 umeenda siku moja. Rudisha hela zako. Lazima ni hela. Hela serikali.
Well, that's the good
If you want to log in, please make sure that I have your email address. Otherwise, when I send out the documentation, you won't be able to get it. Log in kwenye kompyuta yote, make sure that I have forgotten everything. Make sure you register here.
So now we are being out of touch.
Lakini maadamu unanani kwa kipindi kile kile kwa eneo lile lile zitafanana.
Teknolojia inatisha.
Umeona?
Yaani kama kijiji.
Hapo tunaongea mtu kwa barabara.
Niko nazo.
National, international.
Sema siasa.
NASA. Teknolojia inatisha.
Sasa jamani, kuna kujaza hii fomu. Anamalizia kuna nini? Tutaenda kwenye wiki. Kujaza hii fomu wote tunashiriki hapa basi.
Soko ilikuwa kuanzia nani? Wewe
Hata kule mtaala na serikali.
Okay, are all of you ready to continue?
Some have gone out. Maybe we
Okay.
can wait a little bit.
Couple more minutes. All right, that's fine.
Yeah.
I'm going to leave some of these web links on the screen because these will be important for the next few days to use some of these web links. So I'm going to leave these up. So let me know when everyone is back and ready, and I'll just I'll hang on.
Okay, I will let you know.
Thanks.
Sijasimamisha, nasema watu warudi kwanza wote. Yule jamaa ameanza. Anaongea na simu. Tunaendelea. Nani msamgani? Kaeni mkao basi. Hello, Brian.
Yes, how are you?
Fine. Now I think we can continue.
Okay, great. Thank you. So I wanted to share with you a few links that we can use in the next couple days as we bounce through these various tools. So the first one at the top of the screen is a Google Doc that I created for questions and answers. I made a little link to it, tinyurl.com, Tanzania-ODC. If you go there, it will look like this, and it's viewable and you can edit it. Anybody can edit it on the fly. So if you wanted to type your own question here, you can do so, and then our team will provide answers. So if you have some questions and there's not a lot of time to discuss them, or if you want to add them at any time, feel free to use this document. I think this will be helpful, and I'll continue to compile this. So use that. Next are the web addresses for the user interface tool and for the Jupyter notebooks. So the first one, you will notice the web address for the Tanzania user interface is the easier one here, 18, 216, 79, 174. That one I'm going to demonstrate for you very shortly. There are some backups that we have here. When you run the UI, if multiple people are running cases simultaneously, it can get slow. So I've provided a few backup web addresses. This one is actually our Strathmore instance. I think this one might be Ghana or Sierra Leone's instance. It's basically we're using some of their dedicated computational time to run your Tanzania use case. I mean, the way we've got this all set up, it's one data cube. It's just you use various computational resources to point to that data cube and run test cases. So this is the one we're going to focus on now. Oh, let me go back. Is the Tanzania user interface 18, 216, 79, 174. I'm going to show you a demonstration of how to do that, but we'll come back to this page at the end of the morning, at the end of our session here today, so that you have this, because I'm going to want you to try to test a few things between now and when we get back tomorrow at the same time. And then the bottom one is the Jupyter Notebooks. It's the same as the address above, but you add a :8000, and that takes you to a different area, and the password is ARDC user, and I'll be showing you a few demos there as well. So I'm going to move on, but I'll come back to that and make sure that you have these addresses for the future. So let's talk about this thing called a user interface, and I'll jump over and demonstrate it in a moment. As I said, this is a GIS tool for high-level analysis and case studies. You do not see the algorithms, so you don't need to understand Python code. Everything is menu-driven and everything is built in. It's a software module that can be modified. So if you do have some sharp computer programmers, they could recreate this user interface, or you could create your own user interface to do anything you desire. Right now, it's linked to Landsat 7 and 8 data sets, things that are in our cube. You can view things in time and space extent, just like you would any other part of a data cube. You can do some subsetting and download cubes offline. You can output results in GeoTIFF, which is very interesting, by the way, because if you output a result in a PNG format or in a GeoTIFF format, you might find that very useful if you go and use that in QGIS or ArcGIS. You can create a product and then go look at it elsewhere with a very intense GeoTIFF file. It allows a little bit of single pixel analysis. I'll show you what that means. And each country has their own UI with a view of their cube. That's the way we built it at this early point. So when you get there, it looks like this. It actually asks for a login. So you just create your own username and password. That's just so that we know who's logging in and using it. But it's free and open. On the left-hand side is a details pane. This window pane sets up your case study. When a task is running, in the bottom left, it'll give you a status of what's running. Along the top is the menu bar. So you're going to see Data Cube Manager. Will tell you about where the cubes are. The tools, these are the algorithms, and then a task manager. Everything that runs gets put into this GIS viewport, and this allows you to zoom in and out. So when you get there, you're going to see something that'll show us where the data cubes are. I'm going to show you that in a moment. It's going to show you a list of the cubes and the spatial time extent, and allow you to do other more complicated things like ingestion on demand and subsetting the cube. Chances are you won't do much of that. Chances are you're going to be focused on these things, which I'm going to call tools and algorithms. Remember, we were talking about urbanization. There is a built-in urbanization algorithm, the build-up index NDBI. That's built in. I'll show you how we can run that. And there's a whole lot of other spectral indices like vegetation index and enhanced vegetation and burn ratios. All those can be run. Fractional cover is another really good one, which is actually pretty good for the mining activity. And then I'll show you some examples where we do general mosaicing, cloud coverage, and water detection. So I'm going to jump over and demo, and then we'll come back to this. Let me see if I do this. We'll come back to this when I do the Jupyter Notebooks. So let's just spend a little time here. Tomorrow, when we start our session tomorrow, some of the guys on my team from Analytical Mechanics, part of the NASA DataCube team, they will be walking you through some more detailed case studies using the user interface tool. And based on what we've heard today, deforestation, urbanization, and mining activity, I'll ask them to focus in on those so that you can see how you can use the user interface tool to tackle some of your needs. So here I am, I'm at the tool now. If I click on DataCube Manager, DataCube Visualization, I can see the cubes. And in the case of Tanzania cube, if I just click on the Tanzania cube and go over to the left, I have Landsat 7 and Landsat 8 in my cube. If I click on Landsat 7, what pops up is the extent of all that data. What you see is the data starts in 2000 January and goes through January 2018. So like I said, you've got 17 full years of data there, 9,000 scenes of data, which by the way, 9,000 scenes of data would cost millions of dollars and take you a very long time to download if you had to do it on your own. So there's a lot there, and you can do the same thing. So this is just to allow you to browse the data. So if you wanted to, you can go run an analysis on Ghana. I mean, that cube is accessible to you as well. And there's transboundaries. So if you've got Kenya and Tanzania, and you're looking at something along the boundary, water, reservoir, Lake Victoria, any of these things, that can be done across the boundaries as well. So let me show you the tools. These are the things that are most important. So the first one I'll start with is I'll just do a mosaic, a custom mosaic. So I click on there, here's the cubes, I run Tanzania, and let's say I just want to study this area around Dodoma in the capital. I zoom in here, and I would always start with a small area. Be careful that you don't pick that huge of an area to do your analysis, because it'll choke. It'll take too long to run. But I just want to start small. But Dodoma is large enough as it is. But let's just say I wanted to click on an area. So you click and then you drag to create an area. So here's an area I have over Dodoma. What I'm trying to do is create an analysis where I'm going to create a median mosaic. So I'm going to filter out the clouds. I'm going to have true color. It's going to come back as a true color image, which you'll see on the screen is not the prettiest image. Median pixel. I'm not going to do a time series right now, and I'm going to pick a year, and I'm going to do 2017, and I'm going to go back to January 1, and if I click January 1, 2017, it automatically increments it 1 year, and I click submit. So here's what's happening. In the bottom left, it is running this task. Think about what this is doing. It is taking all of the Landsat data for the entire year of 2017, filtering out the clouds and creating a cloud-free mosaic, and there's the solution. And this is what you get. So you see there's some vegetation over here. You see the urbanized area tends to be a little bit dark. But that right there, after I've run that, if I go over to the results tab, I can see a little bit more about what I just created. I click on the results tab, and here's what I get. It showed me this thing ran in like 10 seconds. Here's the latitude and longitude extent. By the way, you can put a lat and lon box. You can define that specifically by punching the numbers in. You do not have to use the mouse. There's my time range. I ran it for a year. I did a medium pixel mosaic. And if I want, I can click on this, which is highlight no data. and it would come up as either red or yellow. Well, that tells me it's a really clear mosaic. So let's go down and see what the scene is made of. This is all the acquisitions that are in this final product. So basically, December of 2017, there was a scene that was 81% clear. There was an 84% clear, 83% clear. These are actually pretty good. That's telling me that this part of Tanzania is not very cloudy. It's actually quite nice. Now, there's a really cloudy scene. That scene was 2% clear in March of 2017. So in February or March of 2017, probably your rainy season, that was a very cloudy image. And so what it did is it took all the best pixels and it created a median or a midpoint, average type thing of that, and this is what you get. And in the very bottom, I want to show you also, it shows you there's 12 scenes in here, and the final product is 100% cloud free. So the last thing I want to do is show you, if I wanted to output this, how do I output this to something I care to use? The first thing you must do if you run several cases, you must click on the case that you want to output. So I clicked on it, and then I come down here and I download selected. I can download a bunch of things. I can download the PNG file, which is the image you see right here. So let's just say I do that and I hit download selected. It'll start the PNG file. It has just created it. I could click on that, open it up. There it is. And there's the PNG file. And you can see it's pixelated and you get all the pixels out of there. Now let's say I wanted to do a detailed analysis. I could create a GeoTIFF download and I hit download select. And that one was bigger, and that one was, I think, 5 megabytes. I just saw it. It happened really quickly. But if I go to my desktop, that GeoTIFF was 5 megabytes. I could load that GeoTIFF into my QGIS or ArcMap or ArcGIS tool, and I would have a perfectly cloud-free mosaic for 2017 that I could do a further analysis on. So this is how you output things. So let me stop there. I'm going to demonstrate one other thing, which would be, I'll go over and I'll do a quick urbanization one, and then I'll do one with water in a moment. Any questions at this point?
Yes. Yes.
Hello, Brian.
Hello, Brian.
Yes.
Wait for the question.
Yes, I just want to ask a quick question.
Yes.
On this data cube, the image we are downloading, I was not quite clear on the date, the year and the date. Are these actually the satellite image which resolution mostly are we going to get?
You were breaking up a bit. I didn't quite. So you had a question about the image, the final product that's shown here?
Yeah, the final product. Are we getting the true color of the image, the satellite image, and what the resolution are we able to zoom in?
The final resolution is typical Landsat resolution. It's 30-meter scale, 30-meter pixels. So, that's typical what you get with Landsat. What gets shown on the screen, you have to be careful. It's a little hazy. You see, it's not real clear. And the reason is for rendering purposes in our code, we do not put a super high resolution image up there. When you pull the GeoTIFF out and download the GeoTIFF and load the GeoTIFF up in something like QGIS, it's a lot clearer. You'll have better detail in the image, just to let you know. But yeah, basically this is a 30-meter true color red, green, blue image you're looking at here. If I wanted to, I could, I'll do a false color one. So let's just say I wanted to do SWIR 2 near green and run the same image. I'll just do that real quick and I'll show you a false color. So what it's doing is it's assigning red to the SWIR 2 band, green to the near infrared band, and blue to the green. And notice what I get here. This is slightly different. So it shows some of the urbanized areas gets enhanced, some of the vegetation looks darker. So this is what we call a false color image. It's basically just assigning colors to the various bands in the Landsat product. Any other questions? Hopefully I answered that.
Yeah, thanks.
Another question.
Go ahead.
Excuse me, Brian.
Hmm?
Most of us here are using ArcGIS and
Okay.
GIS software. So you have said that do we really need to use QGIS instead of using ArcGIS?
Oh, you can use ArcGIS, no problem, no problem. It's when you, like you see the GeoTIFF that I just produced, if you produce any product and output, you know, I click on like what you just saw me run there, and I click on that, and I come down here and put Mosaic GeoTIFF download, you can then load up that GeoTIFF result into ArcGIS and do all kinds of analyses, right? So it does, so the tool, what it's doing, the powerful thing the tool is doing is it's creating a cloud-free mosaic for you, right? It's filtering out the clouds out of these 12 scenes, and it's creating a nice little image over the spot that you want, cloud-free. So you could do, let's say this one I did was 2017. So let's say I go back and say, all right, I'm going to do an analysis. I want to compare some information from 2017 with some information from 2005. Now I go back and I run the same analysis for 2005. I'm going to run it now. You'll probably see a difference. I'll bet you Dodoma's a little smaller. And there it is. It just ran pretty quickly. It's got, you got to be careful, get some banding through it. Those old Landsat 7 bands can be a bit ugly. But notice the vegetation in the right changed. Dodoma's a little smaller. I could now come to the output. The case I just ran is right here. It was only 5 scenes back then, so not a lot of scenes, but it's 100% cloud free. I could go download that GeoTIFF, and now on my desktop, I have 2 GeoTIFFs, one for 2017 and the second one I downloaded for 2005. I could pull those into ArcGIS, ArcMap, and do any analysis I want comparing those 2 years. Does that make sense?
Yes. Okay. Thank you.
Yep. So yeah, it gives you, now, so again, I would suggest the following. Start small when you run an analysis. If you know you got a big area you want to analyze, start small and then build it up a little larger just to see how long does the code take to run your case study, because it can be a little slower because of the graphical interpretation. So let me jump over. Oh, there's another question. I'm going to do urbanization. So let me do urbanization, and I'm going to zone in on Dodoma here, urbanized area. This is urbanization Dodoma, and let's just do 2017, April, or actually I'll do January. I'll go back January 1. So again, I'm picking the date range. I just used my cursor to pick my lat-long bounds. You can do this by hand if you wanted to. I'll do a median pixel, and I'll run this right now and see what we get. So this is an urbanization query, and this is the NDBI, if I'm not mistaken. Is that correct, my guys? I think they'll confirm that. So notice what it looks like when it zooms in. The urbanized areas come up as these bright green, and the other stuff is red. So this might not be an urbanized area here to the north east of Dodoma, but it might be a bare soil area. This is urban in here, everything here in green. But you could, again, you could take that out and you could pull out that GeoTIFF and look at the details of that NDBI product that comes out of that. So this is just one. I find the products that I get, and I'm going to show you in the Jupyter Notebook, they look a bit better than this one. So let's try another case. I'm going to do, let me go over and do water, which I find to be quite interesting. So we're going to take some water near Dodoma. Let's look at this Lake Salonga. I'm going to take the whole lake. So here's what this analysis is going to do. I'm going to run this analysis for the entire time series. I'm going to run it from 1999 through the end of 2016 on all the Landsat data and water detection. This one runs pretty rapidly. So this is 17 years of water history over the lake. And what it's going to calculate for us is the percent of time that any individual 30-meter pixel has experienced water. So what this will tell you are some details about areas around that lake that have grown in size or shrunk in size in terms of the lake borders. You'll start to see regions that have water surrounding them during rainy seasons. You'll start to see changes in water coming in. So perhaps this river right here is probably one of the rivers that feed the lake. So give this one a second. It usually takes about a minute or so to run. So if other people are accessing it right now, it might be a little slower. Give this one just a second, and then I'll come back to it. So again, this is a water case study. We'll come back and do the Jupyter Notebook stuff probably tomorrow. I just want to focus on the water stuff now. Again, if you have any questions or anything, feel free to use the Google Doc for your questions. And these are the links that you're going to be, you're going to want to use these links for the next couple days. So this user interface I'm demonstrating for you, I'm going to ask you after we're done today, I want you to try this link here, your Tanzania link. If it tends to be slow and there's a lot of people running, use these backup links here as other options for you to test out, because I'm going to give you a few things to do today. Before we get back tomorrow, I'd like for you to try to run this on your own. Oh, is this done yet? Let's get close. Give it just another minute. We'll go. Are there any questions in the meantime, as this is taking a few minutes to run? Sometimes these run quick, but I picked 17 years of data over a fairly large lake. That's why it's taken a few moments to run.
Brian?
Yes.
Well, you apply
you're breaking up a bit. I can't quite hear.
To the selection.
I couldn't hear the question. Is anybody else could repeat it, or perhaps get closer to the mic and help a bit?
No, Brian, that wasn't a question. It was
no question.
It was just a suggestion that anyone can ask. Nobody has a question.
Brian?
Yes.
Perhaps maybe I'm asking a question that will be having an experience maybe tomorrow or the after tomorrow. My interest is, as what I've said earlier, for example, if I want to go to the session and testing the authenticity of the data.
Mm-hmm.
Here now, is there any tool here that at least I can draw a polygon from what I've seen, for example? Perhaps I've run the run and then come up with the results. And I want to, if I want to draw a polygon, such a polygon, and go down to verify to see the authenticity. Is it possible to be done here?
Yes, and how large is your polygon? So right now this
A smaller one.
Yeah, this system we have here just does lat lon, square corner boundaries. If you had a shape file, a more complex polygon, that has to be done within the Jupyter Notebook environment. But if it's just a square polygon, it's easy. If you know the lat range and the longitude range, you can just enter it into this box and it will create it for you.
Okay.
All right, so here is the result. This is quite interesting. And by the way, I have not run this lake before. I haven't tested this whatsoever. So here's what this is telling me over 17 years. And maybe some of you can verify this because you may know more about this lake than I do. The only part of this lake, and so I'm going to click over here, by the way, on the right-hand side is the legend. Click that, and there's the legend. So let me pull this over. So the legend is telling us that areas that are blue are water 100% of the time. So this lake, actually, some of it's not dark blue. So I would say between the year 2000 and 2016, this lake has had dry periods quite frequently. And this lake has only become large, and we can see what the dates are in general. But this area in the center is water most of the time. This area around this perimeter in green is water only 30 to 40% of time over 17 years. And then these areas in red are extreme events that are water only 0 to 5% of the time. So this lake is dynamically changing substantially. It appears that there was a dry period and that it was not water for much of the 17 years. So how do we know this? One example we can do, I'm going to turn that legend off, is there's a pixel drill tool in the top left corner. It looks like a little eyedropper. I click that eyedropper. I come onto my image, my result, and I click on this result, and I'm going to click on the yellow portion right here, which is water like 10% of the time, and I click it. It is going to generate a time series plot for that pixel that I zoomed in on, which is right there. And again, that's going to be water 5 to 20% of the time. So we'll give this a moment to run. And when the result is created, it's going to give me a time series plot over here of that. What I'm going to ask all of you to do today when we're done, because we're going to be done here in about 10 or 15 minutes, is I would like all of you as your homework for tonight is to do the following. I would like for you to do this. Visit the online user interface tool, create a small cloud-free mosaic like I did. So pick a year, pick a spot, play around with it, see if you can generate a mosaic. I also want you to find a different area of water and run the time series product that I just created and use the pixel tool that I'm using right now to look at the data and see if you can find anything interesting. So here it is, and the plot has been generated on the right-hand side. Now, let's look and see what this says. The bottom is something called clear mask. It just tells me whether I had clouds or clear. If it's clear, it's 1. If it's cloudy, it's 0. So notice I had a bunch of clouds and I had a bunch of clear scenes too. It's probably about 50-50. So this is a fairly cloudy spot, but not terrible. Now go up to the top image. This is water, non-water over 17 years. So here's what happened. This little spot in yellow was only water in the very beginning of the time series from 2000 back to about 2003. You can see the dots here said it was water. Sometime around 2000, maybe 2 or 3, it then reverted to non-water, and it's been mostly non-water except for this one single event in 2007, might have been a rain event. But the bottom line is This portion of the lake does not exist today because it's showing it's been non-water since 2003. So right now, your Lake Salunga was much larger. So historically, I can see that this lake was much larger back in the early 2000s than it is now. Is that correct?
Yeah, good.
Mr. Brian.
Yes.
Yes, I have a question.
Mhm.
Is it possible to convert this unit into UTM?
Into UTM coordinates versus Latlon?
Yeah.
Yeah,
No,
we don't have that feature built into the user interface. I'll have to ask my technical team about that. But that's something, yeah, because I understand a lot of you like using the, your local coordinate system, right? UTM.
yeah.
So you're probably more familiar with the easting and northing coordinates, correct?
Of course.
Yeah. So I'll ask my team to look into that to see how we do that UTM conversion. Right now, I would just suggest if you've got a way to convert it to Latlon, then you can make your own bounding box. Let me run one more quick one as we wrap up. So I'm going to pick a different spot. So let's go north of or south of Dodoma to this little reservoir down here, and I'm going to run a little test case down here. I'm going to run a case right over this little feature of the reservoir, and I'll do the same thing. Maybe this one will run a little quicker because it's smaller. But what I want you to do as part of your homework tonight is to try to play with this online user interface. See if you can make yourself a cloud-free mosaic. See if you can go through the results tab and the output tab, maybe download yourself a GeoTIFF, load it up into ArcMap, and just see how it works for you. And then play with this water extent tool as well, which I find to be really interesting, the water history, especially in places like reservoirs and water bodies that are changing significantly. So this one's going to be done here in just a moment, and we'll take a look at this. So again, if I look at where I'm zoomed, this is the Matera Reservoir just south of Dodoma, a very large reservoir. Here's the case study we ran before. This study is much smaller. So here's the region. And this is interesting because if I look at the normalized percentage, most of this is green, which is weird. That's only 20% of the time it was water. And then there's some stuff in here that's a little lighter, and then the main reservoir here. So I'm guessing this reservoir was built sometime during this time period, much of this water. So I'm going to click on the eyedropper and go right here perhaps and see if the time series tells us a bit more about the history of this reservoir. Because if this was water today and it was water 100% of the time, this would have been dark blue. And since it's not dark blue, it's telling me that this portion of the reservoir does not exist. It probably doesn't exist today. It's probably a lot smaller than it was, which was similar to what we saw in the lake. So the lake that we just analyzed just to the west of Dodoma appeared to have dried up quite a bit historically. So this thing is running this time series. Just give it 1 second, and then we'll end there today. When we come back tomorrow, just as a reminder, the first thing we'll start off is to answer any of your questions you might have about using this tool, and then I'm going to have my team, my guys are going to go through the user interface tool and run some more examples for you. They might do some more mosaics, some more water, some more indices, perhaps over areas of interest for you. And then we'll spend the latter part of tomorrow's session talking about Jupyter Notebooks and some of the things that you're going to be able to do with notebooks. Oh, here we go. So This one's interesting. So this little part of the reservoir here where the dropper is, and by the way, I can tell where the dropper is if I put my mouse over it. The lat lawn is at the top. So notice the lat lawn as I move around tells me precisely where I'm located. If I go up here and look, here's what's happened. This little part of the reservoir was water from 2002 to 2004. Then it dried up from 2004 to 2008. It was water again from 2008 to about 11, dried up again, and now appears to be water again. Very interesting. So this part of the reservoir here has cycled over the years during dry periods and wet periods. And so this is a very dynamic bit of water here. So if this reservoir is important for drinking water and the volume of the water within that reservoir is important, you can start to calculate the volume of water over time and get a better indication of the impacts of drought or the impacts of, rise and fall of the reservoir size. All of that can be done because you could run that analysis on a much bigger scale for the entire reservoir. And then I can show you how to do that in a Jupyter notebook where it counts the number of pixels that are water and starts to do a time series plot. So I hope that was interesting today and at least got us going and thinking about what this data cube can do from a user interface perspective. I'd like for you to give it a try and play with it a bit. And we will come back tomorrow and do some more of the user interface and talk to you about these things called Jupyter notebooks. So I'll end there today. And if there's any other questions, I'll take them now.
I have a question before you finish.
Mm-hmm.
Hello?
There is a question.
Yes, go ahead. I thought I heard. Yes. Yeah, if you can get closer to the mic. I just heard you say I have a question. That's all I've heard.
Yeah. Yes, my question is about predation and data. Is it possible to create our data on this application?
I'm not sure I understand the question. Yeah, could you repeat that?
And normally when working with this spatial maps, we have some sort of projections. So I see that we're just working without some sort of projection, and we have got projection based on different regions and zones. And now we have got the data that describes the geographical location of the area. So before you start working with the map, you can describe and you can set and fix the specifications basing on your region. So is it possible to do that with this?
Yes, I will ask my technical team to provide a response back on that. But I think what you're asking is it possible to use different data projections, right? The datum projections in different parts of the country. So are you saying that you use a different UTM coordinate zone for different locations?
Yeah.
Yeah. So here's what we do. The data cube, when we store the data cube in its native format, what we try to do is not resample the data, but to store the data in a single format. So we choose the UTM standard projection that's used by Landsat, right? It's just the UTM WGS84, very standard. If you wanted to run an analysis, you could run, and my guys could help develop the script, but you could reproject the data on the fly to a new projection, then run your analytical case study. I don't know, maybe you're creating a cloud-free geotiff or something, and then it would produce a geotiff for you in the projection you desire. Is that sort of what you're trying to get to, is creating these products in your UTM projection?
Yes, another question. Hello?
Yes, go ahead.
Yes, another question. Yeah, assume that I've got my satellite image or map. Is it possible to publish my map on the cube and then I can make analysis based on my own map and satellite image?
So you mean a shapefile?
Yes.
Yes. That has to be done not within this user interface tool. It's something we probably will be adding someday to the user interface tool because we've had this question a lot. Is the ability to use shape files for identifying, a geographical area. So we will work on that, and I'll have to talk with my technical team to see where we are on the shapefile idea, and maybe that's something we can demonstrate for you in the next day or two. So it sounds like there's two things. Number one is the shapefile, right? Your own map that defines a region of interest. And the second thing would be a reprojection of the data into your, desired UTM data.
Yeah. Yes. Only
Do
two
you
questions.
do you know which datums you use? How many do you use, or do you just use one specific one for one spot?
No, we have got our data. Maybe Uganda will send you our data on some sort of our specifications, right?
Yeah, if you send us that datum, we could. Yes, just send it to me by email, and I'll ask my technical team to take a look at it. Because what we could do is we could build you a Jupyter notebook, a little script that.
By the way,
so let me ask you.
Yes, we can use
do you want to take the data and use it and create like a GeoTIFF product? Is that what you're interested in?
Yeah.
Do you want to do your own analysis like in ArcGIS, or do you want to use some of these tools? So I guess what I'm trying to get at is how you will actually use the data. If we use your shapefile and use your datum, what is the next step? Would you do some analysis outside of the tool, or would you use some of these algorithms?
I think I was trying, maybe I could hope to use to publish my map on this cube, and then I can try to measure some sort of accuracy and discrepancy between the satellite image, existing satellite image or base map that I have, and Google map or this one that you are using.
Got it. So you're looking at just like an RGB output, an image. Basically, you're going to probably take this into ArcMap, right, or ArcGIS, and look at the
QGIS.
QGIS.
ArcGIS.
ArcGIS. So you're thinking about creating maybe a cloud-free mosaic, right? Like a cloud-free image, and then comparing it with other maps that you have in the region. Okay.
Yeah.
I will get my guys to take a look at that. We'll try to build you a script to do that. So you need to send me, if you send me your datum, your projection, that will be very helpful. And even a shapefile, if you have a sample shapefile. So your shapefile, your data UTM, and then the output would be a GeoTIFF output, and we can show you how to do this GeoTIFF for a mosaic. And then you could use this process anywhere you wanted and any time period you wanted, right? Because you could do this for multiple years. You could create a nice clean image every year and start to look at the output. Okay, yeah, we can easily we can do that for you.
That's good. I think.
Any other questions?
Brian.
Yes.
Can you go back to the Lake Surunga?
Mm-hmm.
It was very, very interesting. It was very, very interesting. Lake Surunga.
Yes, Solunga, right.
Okay, can you go back, please?
Yep. So let me see if I still have that up there. I don't know if I erased it. Nope, it's still there. So this was the Lake Solunga map. Yeah, go ahead.
Of course, from the analysis that we have seen, and of course, I don't remember, is it 30% or 10% of which the water has been lost? And I'm trying to think, maybe if we can predict now that if this situation goes, and maybe in 20 years, 50 years to come, this area will remain with water, and maybe won't remain with water. And according to this now analysis, we have to find a way on how we can make sure that this water, the water body is
right, sustained, because I'm guessing this is a fairly large water body and serves a pretty, broad area, right? And it's certainly been drying up quite a bit. So one thing I can do is I will have my guys take a look at this Lake Salunga, and we have a water Jupyter notebook that we use for Lake Chad that basically takes this area around the lake and it runs a time series calculation of the total volume of water over time. And that will be very telling, right? That will show you significant, how much the lake is really drying up and how things are changing. So we'll run a little case study for you. And that, I think, then once you have that Jupyter notebook, you can apply that Jupyter notebook to any other water body in all of Tanzania. You can just reproduce it and rerun it. Does that make sense?
Yes, of course. What I'm thinking about is that if even people from the Ministry of Land, they may be very interested to update the base maps of which we have. Of course, I think the base map of which we are having, it may be showing the water body. The water body is maybe covering the whole entire, even the area which is not having water at the moment. So if we can have this information, we can update our base maps, and then of course, we can have at least the current data from our base map we're using.
Yeah, very good point. Very good point. Because one thing's for certain, it is fairly easy to detect water from the satellite imagery. That we're very confident. We get 97, 98% accuracy in water detection. So it's a really nice thing. And what you find is when you go to Google Maps, it is often reflective of where they thought the water was a couple years ago, right? The maps tend to be old, and when things change and this lake is changing over time, you need to update your maps in terms of the water extent and so forth. So yes, we can help you do that. Yep.
And then of course, what I'm still wondering, what is really happening now in that area which has lost the water? Is there any economic activities which is ongoing there? People are farming. What is exactly going on there? Also, it's
in the red areas.
Yes.
Okay, so here's what this is. If you zoom in here, this is interesting. Any of these areas that are red, so these are along the perimeter of the lake, these are rare flood events on the order of 0 to 5% of the time they were water. And what that tends to be is one severe rain season. So here's how you determine this. You zoom in on an area you might know, and you might say, okay, this little spot here, I take my eyedropper and I click on that spot and I let it run. So it might take a few minutes to run. And what it's doing is it's going to show me a time series plot for that little area that's red, which is a rare water event. And we'll be able to see precisely what year that was water. Now, something that's yellow over here was water more frequently. I will bet this area right here has seasonal flooding during the rainy season. This area here might have been wet 1 or 2 times in 17 years. So these are the kind of things you can get out of this time series analysis. It's really quite telling when you see it. And if you see some analyses of like areas we did for Lake Chad, it's amazing how complicated. I mean, even this area down in here is pretty complicated. So We'll give this a moment as it's running, but I hope that answers your question. Yes, some of these infrequent little spots like out here. Oh, there it is. It just came up. Water, this little spot right here, this little dropper over that little spot, which is this precise lat lawn, was water one time in 17 years, and it looks like about 2010. Now, if you want to know exactly when it is, you could come to the output file, and you could click on the output file, and you could download it, and then go look at it in, like, I think you can outload it in CSV. No, it's, I think there's a way to actually get the precise date out of that. But anyway, there it is. It's one event in 17 years.
Okay.
So that was probably just maybe just a really rainy season in 2010, and water was lying in this area around here. But then the rest of the 17 years, this was dry. So it's pretty interesting. You can see the rarest of water events with this analysis tool.
This is very interesting, Brian. Thank you very much.
Sure. So it sounds like there's a couple things we're going to do. We're going to investigate this shape file and data, UTM. We're going to put together a Jupyter notebook to do some time series water volume assessments for you. I think that one will be really interesting. And then we'll look at, some of these other case studies like deforestation, urbanization. So I think over the next couple days, we're going to show you some really interesting ways for you to interrogate the data using either this user interface tool, which is one way, or to go into more depth of detail, we're going to show you how to build it in a little bit of a Python script, which I promise you is not that intimidating. You don't need to be a super programmer to do it. It's something you're going to be able to do.
Thank you.
So let's end there for the day, and we'll come back tomorrow at 7 a.m. my time, which I believe is 2 p.m. your time tomorrow. That sound good?
Yeah. 2 p.m.
All right. I'll leave this on the screen here for a moment. If anybody wants to write down those addresses to check it out, I will be talking with my team a bit about how we can put together these ideas. All right. Well, thanks for the day today. We'll come back, same exact spot tomorrow, same web link. Have a good evening.
Thank you, Brian.
You're quite welcome.
Okay, thank you. Neno la mwisho au bado yupo? Hello, Brian.
Yes.
I probably won't discuss anything. I think somebody here say something about how they feel about today. I requested everyone to stay at home. That was
Somewhat.
how we are doing. We need to improve. But I think the line is everybody needs to shoot their questions when they have today. That's the best way.
Yeah, you're breaking up a bit. If someone's asking me a question there, it's really broken. I have a hard time understanding. Was there a specific question?
No.
Okay.
Saying to the team here that it would be best if everyone, whenever they have a question, they can just ask it, because that's the best way to go through this. Otherwise, I'm for feedback on the form today so we can see what we need to improve tomorrow.
Excellent. Yeah, that would be good if they can compile some questions, and if they want to use that Google Doc at the top of the web page, if they have a new question and want to add it in there, let's use that, and that way my team can see your questions. If you come up with something early tomorrow morning, we'll be able to take a look at it and see it. So this is good. It was a good start. There's some really good interaction. I'm very pleased to hear some of your interest in this and some of your use cases. So I think we have a good path forward.
Okay.
Okay, thanks everyone.
Yeah. But